Good afternoon and welcome to the Orion Flight Test Status and Overview Briefing. We are less than 2 days away now from launch and we've got a great lineup here to tell you a little bit about what to expect on launch day. So we're going to start here with the NASA Program Manager for Orion, Mark Geyer. And then we'll hear from the Lockheed Martin Orion Program Manager, Mike Hawes. And then we will wrap up with the United Launch Alliance Director of Mission Management, Ron Fortson. So we'll start with some opening remarks from all of them, and then we'll take questions here in the room. So, Mark.
Good afternoon. Thanks for coming. I've got a few slides. I'm going to talk a little bit about what Orion is. I think most of you know that, so I'll go through those fairly quick, and then we'll talk a little bit about some of the stuff that's happening, and then I'll pass it on to Mike. So this is a picture of the crew module when it was in the ONC, before we put the launch abort system on it and before it rolled out to the pad. And so I like this picture because the EFT-1 is really fundamentally about the crew module. It's the core of Orion, and those are the key systems that we're testing on this flight. It's also a great picture of the back shell tiles. Let's go to the next page. So on this flight, we're on a Delta IV Heavy, and I'll let Ron talk about that, but this is a great rocket for this test. It gets us to the high altitude and the velocities we need to test the heat shield, which is the primary objective of the test. And it's a beautiful rocket. We were out there seeing it today, and it'd be a lot of fun on Thursday to see it go. So next page. This is a picture of Orion in the flight configuration. This is actually the way it'll look on EM1, the next flight, because this actually shows the solar arrays and the radiators on the service module that we'll actually have by the next flight. But it gives you a sense of what the integrated system looks like in flight. Orion's built basically to go beyond low Earth orbit. It's an exploration spacecraft, and in concert with the Space Launch System, which gets us to those destinations, we're going to be able to explore the regions around the moon and then out into the solar system, including Mars. So Thursday is the beginning of that journey, testing key systems, the riskiest systems, I would say, for Orion before we have any people on it. Next chart. So Mike will go through more of these details, but we're going to test separation events. There's several of those, like the service module fairings, the launch abort system, jettison. Heat shield is the big one because the Delta IV gets us high enough to push on the heat shield about 84% of a lunar entry velocity, so very close to what we expect to see. We're going to see high radiation events as we go through the Van Allen belts. It's good to test the avionics. And the parachutes, of course, are key for slowing us down. A key part of keeping the crew safe when we return to Earth, and so we'll be testing that system too. Next page. I think this is an example of, this shows you the full configuration of EFT-1, and I was going to point out a little bit about what's on EFT-1 compared to what we're eventually going to have when we fly people. So if you go to the next page. The launch abort system on EFT-1 is basically a flight launch abort system, except for there's no abort motor and no attitude control motor, because we're not going to test aborts on this flight. The third motor, which is a jettison motor, which is the motor that actually pulls the LAS off the top of the crew module in a nominal flight, that one will be active on EFT-1, and we'll actually be firing that jettison motor about 6 minutes after liftoff. But the structure is exactly what we expect to fly with people. Crew module I talked about before is the guts of this test. It's a heat shield, primary structure, back shell tiles, parachutes, guidance, navigation, computers, all the things that we're going to fly people with eventually. Those are the things we're flying on EFT-1, and that's the core of the test. Next chart shows the service module. For EFT-1, it's primarily a structure. We're testing how it interfaces with the crew module, and that we can effectively do a crew module service module separation, which involves 6 pyrobolts firing. That's a key part of the test. But the rest of the service module is fundamentally just a structure along with the fairing. So we're testing fairing separation and crew module SM separation on EFT-1. On EM1 and beyond, the back end of the service module will actually be provided, the back end of that piece that's highlighted right now, which would include the prop system, the radiators, and the solar arrays, will actually be provided by ESA. So that's the big change as we go from EFT-1 to EM1, is adding ESA as a partner on Orion. The next chart just shows you the adapter and the fairings. The fairings are actually the picture's a little deceiving. The fairings are actually wrapped around the service module in the middle when it flies, and they're actually jettisoned. That jettison is something we will test on EFT-1. On the next page, I think that might be it. Yeah, I did want to say, so Thursday's a huge day for us, obviously flying Orion. It's the beginning of exploration. It's the beginning of actually putting Orion into space. The beauty of it is it's a flight test. It's an unmanned flight test. A part of me hopes that everything is perfect. We land, high fives, everybody has a great time. But really, on a flight test like this, if there are subtleties in how the vehicle behaves with the environments, or subtleties with how systems actually behave with one another during flight, my hope is that we find that on this test flight. That's what it's all about. We want to discover things that are beyond our modeling capability and beyond our expertise, so we can learn it and fix it before we put people on board. So that's why Thursday is so important for us. So with that, I'll pass to Mike Hawes.
And I'm glad that Mark kind of ended on that theme of the test flight, because that's, it's different doing a test flight than doing a mission. And this whole flight profile has been structured to do test flight activities. And so that's kind of key to how this whole thing has come together. It is a big deal. And from the standpoint where Mark says it's the first step to exploration, so this is the first human-rated spacecraft that's gone beyond LEO in 42 years by my count. And so it is a big deal to get out beyond the Van Allen belts, to get out in that space environment. So why the test flight? The test flight is to be able to take critical technologies and pieces and test them in that space environment, not just in the LEO environment, but out further where we see things like the effects of the Van Allen belts. And we fully expect to see effects of those, whether or not we actually get computer upsets or not. We've designed a system that recovers from those, that is tuned to be able to have that response. So that's what's driven this whole mission. And if you show the graphic that I have, just gives you a real top-level sense of the mission. We launch here on Thursday morning. We do one close-in orbit, and then the upper stage of the Delta IV pushes us out, and that's about 3,600 miles. And as Mark said, when we re-enter from there, we separate from the upper stage. Orion re-enters, and we get about 84% of a lunar re-entry velocity, which translates into the heat load, which tests the heat shield. So using the Delta IV Heavy, the systems that are included in Orion for this flight are all about those test flight parameters. Mark mentioned several of them, the key separation events, the heat shield performance, but we're also we're using our propulsion system to line up for the reentry positioning. We're flying with much of the software that we will fly when we fly crew. So we're actually demonstrating much of the system's capability of the crew module, but demonstrating those key technologies in the space environment where it's very difficult to duplicate that on the ground. Some of the things that we're not doing, obviously, is we don't have the full human systems in this capsule, and those will come later in terms of both the displays and controls for the crews and the habitation kind of support systems as well. There's an aspect of this mission that is also very different from a NASA-Lockheed relationship standpoint, in that when NASA decided that they wanted to insert EFT-1 into the program, they chose to do that by tasking Lockheed to be the mission management function to actually purchase the Delta IV Heavy from ULA. And one of the other aspects of that is that we chair the mission management team for these flights. And so the mission management team, we actually started our meeting Sunday night as a prep for the recovery ships leaving port. So we started Sunday night. We've been meeting each day. Mark and I go right from here to the meeting today. And we'll meet again tomorrow, even though we're back on console about midnight tomorrow to get ready for launch. So that's been a unique aspect, but we've also tried to do that as effectively as we can. We have not created additional infrastructure just because we had this role. So, for example, our friends here in Kennedy, the Ground Systems Development Office, are our interface to the recovery forces for the U.S. Navy. They're also in charge of the transport back from the the Navy station in San Diego back here to Florida. The JSC flight control team in the MCC is the JSC team. We're not creating an extra team. We have added support to them. We have our Lockheed Martin engineering support that is independent, but everywhere it can, where it makes sense, we use this blended team. And I think that that's something that when we get done with this flight, Mark and I and our teams will have to sit back and say, what worked really well? What would we change? How would EM1 look different from this? So it's not just a flight test of a spacecraft, but it's also a flight test of how we interact between NASA and the Lockheed Martin team. And with that, then I'll pass it on.
Thanks. Hello, I'm Ron Fordson with United Launch Alliance, and I just want to say, we're really thrilled and honored to be a part of this this mission. The Delta IV Heavy was selected by Lockheed Martin to launch the NASA's EFT-1, and we couldn't be more excited to get this opportunity to do this today. It's been a lot of teamwork, tremendous. You've heard it from all the other two folks. Teamwork has been the key to success to get to where we are right now. Thousands of people have been working thousands of hours to get here. We started about 2.5 years ago with Lockheed Martin. We kicked off this mission and started the production out in our Decatur facility in Alabama about 2 years ago, building this heavy rocket. It consists of 3 common booster cores with each has an RS-68 Rocketdyne aerojet Rocketdyne engine on the bottom of it, and we're looking to take that along with the second stage, which is an RL-10 aerojet Rocketdyne RL-10 second stage, and deliver them where they need to go. That's really, I know you've heard about this is a test flight, but from ULA's perspective, this isn't a test for us. Our objective is to deliver them right where they need to be so they can start their activity. So that's what it's all about for ULA. I would like to show a short video of some of the launch processing that's occurred since we've delivered the hardware here. You can see that's the Mariner. Delivered the hardware. It took 8 days to get here from Decatur. Basically, we offloaded that. That's one of the common booster cores coming off, and we're basically got it on our transporter, and we transported down to the horizontal integration facility that you see right there. Once we get in there, we start doing initial processing of that. We basically take the 3 cores that I talked about, the core and the starboard and port common booster cores, and we mate them together. You can see that's happening there. We're basically attaching 3 rockets together. Then we go ahead and mate the second stage, which is going to put it into that elliptical orbit that they need in order to meet all their objectives. We mate that, then we attach it to the launch mount unit. You can see at the very bottom there, it gets transported out to the pad. Takes quite a few hours. It's only traveling 5 miles an hour, but we got to be careful and make sure we get it there. Once we get it there, there's a fixed pad erector that's underneath the rocket right there, and you can see essentially lifts the vehicle up. Those launch mounts that are on the very bottom of the rocket, that's basically what we're going to launch it off of. Those get attached. You can see here, there's the Orion capsule coming out to the pad. We basically lift it up. You can see it's being lifted into the mobile service tower, and then we stack it on top, and then on Thursday, this is what we're looking to do: put them up in orbit. So it's been a really great effort. We've had quite a few readiness reviews getting to here. Yesterday we had our system certification review where our technical team went through all the risk of this mission and all the hardware mission analysis, all the design activity associated with this mission, and we're good to go. This morning we completed our launch readiness review with the customer. We looked at our launch vehicle, making sure it's ready, as well as the spacecraft, and then we looked at all the range assets, everything that's here to support this mission, and we're ready to go. So we're really excited about that. Out the launch pad right now, there's a few things going on. We're doing all our final safety walk downs with the rocket, making sure everything's good. Like as was mentioned by Mark, we had the opportunity to go out there this morning, and it looks really good. It's in good shape, and we're really excited to launch this on Thursday. So we're finishing that up. We're closing out all the compartments, and tomorrow evening we'll have a weather briefing, which weather's looking pretty good. We'll go ahead and we'll move the mobile service tower out, and a little bit before midnight, team will get on console around midnight or so, and then we'll start the countdown in preparation for the 7:05 a.m. launch. So we're really looking forward to that. As I mentioned, it's been a great team effort from all of us. One of the things from United Launch Alliance is, we really focus on perfect product delivery. It's very important that we get everything right, and we have a relentless focus on mission success, because it doesn't do any good if we don't put the customers where they want to be, and that's really what it's all about. So once again, it's a pleasure to be part of this team, and we're looking forward to an exciting launch on Thursday. Thank you.
Maybe we should give them Ron did a really good job of describing that we had the LRR today. Maybe we should just let everybody know where we are as far as getting preps for launch, so that we have our MMT, L-2 MMT today at 3. Mike and I will be there. Lockheed will chair up, but NASA is a part of that, and I expect there'll maybe be 3 or 4 pieces of open paper, which are really wrapping up reports of tests and the last pieces of closing the hatch and those kind of things. So it's very, very normal open work, really not working any issues for the flight. The folks that are recovering Orion left yesterday. The Navy ships, they will both be on site tomorrow. The recovery weather is also projected to be very good, with 6-foot wave heights, 11-second period. So that's really good for recovery. Looks good for us. So we're green for the recovery conditions. At least that's a prediction for today. Excuse me, it's today's prediction for Thursday. Just to be clear, and Ron mentioned the weather here at the site as far as getting the rocket off on Thursday also looks good. There's some constraints with some rain coming in, but all of that looks really good, and so it's all ticking down. And of course we'll have the MMT today and then one tomorrow just to make sure, but it all looks really clean at this point.
And we would remind folks that for this flight, we have a 2.5-hour launch window. Right. So even the potential for rain that's coming Thursday is likely, the likelihood of finding a spot in that 2.5-hour window to launch, I think, is pretty good.
Yeah, it's a really good point, because you're used to space station launches where you have a very tight window. We don't have that. We've got about 2.5 hours. We launch as early as we can, so we have light here, so we can see the separation events. And then there's also a thermal constraint, a beta angle, solar angle constraint on the upper stage, and then also on the far back end we want to give the guys off the coast of Baja enough time to recover in the daylight. So that's kind of the window. But as Mike said, that gives us a lot of flexibility. If it's raining right at the beginning of the window, we just wait a little bit till it clears and then go. So we have a lot of flexibility on Thursday.
Okay, I think now we're ready to take some questions. So if I could just get you to state your name and affiliation before you start your question, we'll open it up. And why don't we start here in the...
Thanks. Irene Klotz with Reuters for either Mr. Hauser or Mr. Geyer. Is the entire 4.5-hour flight pre-programmed? Is there going to be any kind of real-time controlling of the spacecraft, or if anything is going amiss, is there anything anybody can do? And also, aside from key events like parachute deploying and seeing that the heat shield keeps the spacecraft together to re-enter, will you need to recover the capsule to be able to tell if there was a computer out or anything like that? Or I guess kind of what I'm asking is, what sort of real-time information will you be getting, and will you be able to take control of?
Yeah, no, those are great questions, Irene. So there's a couple aspects of that. The Orion is programmed for the full sequence today, so it can control the whole mission today. But there are a series of, we call them contingency commands, that we have worked, the whole NASA Lockheed team has worked, that the flight control team in Houston has. If there are things that we want to do, if we want to reconfigure systems to put ourselves in the best posture for reentry, for example, the team has the ability to do that. And there's a couple tiers of those. Some of those force a mission management team discussion about taking those actions. Some of those are right within the flight rules that we have all agreed between us that Mike Serafin, as the flight director, and his team can go off and do. In terms of the data collection, I would interpret the second question in a broader form of data collection. We do get some real-time data, but a lot of the data is recorded on board for post-mission analysis. There is also then the need the desire to get the capsule back, both for that recorded data and also for the physical evidence of how we got through the test flight. In fact, we're having the debate now of whether we take core samples of the heat shield right there basically on the dock, or whether we wait till we get back to Florida. So getting the data back, we're going to actually offload the data and do some processing at a Lockheed Martin facility there in San Diego so that we can get quick look data as quick as we can. And we're looking at possibly taking some samples out there. And then the rest of that will happen when we get the capsule back here to KSC.
Yeah, so as far as your question about the computer, we have the full range of telemetry, so we're going to know what systems are up, what's running, what's not, and so that gives us the input to know whether we want to send any contingency commands to change any of the strings, that kind of thing. So we're going to know exactly how the vehicle's behaving as far as the flight systems. And as Mike said, we have what we call DFI, which is 1,200 sensors that's measuring temperatures, vibration, acoustics. We even had a radiometer on the heat shield that's measuring the temperature of the plasma. Those are recorded and not sent down. So there are two types of data that we have. And so as Mike said, we need to get the capsule back to get that DFI, those 1,200 measurements. But as far as how the vehicle's going to go, how it's operating, we're going to know that as we fly. Yeah.
Associated Press, 2 questions. The first is, how quickly will you get the capsule back post-flight to Kennedy? And secondly, it's going to be 4 years before another Orion flies, 3 more years potentially before people climb on board. How frustrating is it to have to wait so long after your first debut?
So the guys they'll pick up the Orion, they'll get it back to the pier. So if we launch on the 4th or 5th, we'll be back here before Christmas with the capsule. They'll basically truck it. They'll get it off the ship, put on a truck that has all the licenses and everything else you need to ship something like that across the country. So it'll be back here before Christmas. We will unload the data, as Mike said, even before we leave, and we're looking at taking some samples even before it gets on the truck. But we'll have it for Christmas here. There is a gap between these flights, and we recognize, that's really a budget-driven question. It's not a matter of ability to build these capsules and to analyze them. It's a budget thing. We understand where the budget is, and that the budget's tight for everybody. We feel really fortunate to be in the budget plan, a bipartisan agreement on the budget plan, and our job is to execute to that plan. So yeah, I wish they would go faster, but I think this is a good plan given the budget we've got, and I think the team's doing a great job executing to that plan. So,
but I would add, we're doing work for that next crew module right now, in terms of getting the primary structures formed, machined, getting some of the avionics, a lot of the EEE parts getting ordered. In fact, we've actually already delivered some cards to ESA and Airbus for their use. So there's actually a lot of stuff that's already in a design and production mode for the EM1 crew module.
Hi, Clara Moskowitz with Scientific American. Can you tell us more about the heat shield? What's new about this heat shield compared to materials that have been used on Apollo and Shuttle? And besides just looking to see that it survives re-entry, what sort of testing will you do to see how the heat shield performs? Thanks.
The material itself is called AVCOAT. It's similar to Apollo, though there were some constituents in the previous version that allowed you to form it that were carcinogenic, so we had to change some of that stuff, and that actually does change the properties. But more than that, it's a much bigger heat shield. Apollo was on 3.7 meters. Ours is 5, and the Orion is bigger, so the landing loads are heavier. They're harder, right? And so that changes a lot of the properties that the heat shield has to survive on landing. So the loads are different. Some of the materials are different. Those are the big things. So one is how it ablates as it comes in, right? We have a lot of models that guess. They're good models, and we've done some arc jet testing out in California. So we have guess about how much of the arc jet will actually ablate during the process and where it'll be the thinnest. So the key part of the test is seeing whether those aerodynamic models were correct and we guessed the right, because that affects the thickness and the mass overall that we're going to use. That's a big part of the test.
And we also have a different structure for this heat shield than I used in Apollo. We have
What's
a
supporting
composite.
heat shield,
Yeah, the supporting structure is a composite shell on a titanium skeleton. And so that's a different methodology than they were able to use in Apollo. So it's looking at the whole integrated system is key to that as well, not just how well the material ablates or.
Hi, I'm Miriam Kramer with Space.com. And this question is for whoever would like to answer it. But I'm curious, first of all, how many people are you expecting to sort of view the launch from KSC? And also, I know there have been a couple different numbers, but just if you could give a general estimate of how much this EFT1 test costs, then that would be great.
So I'm not sure what the current projection is, thousands. But I
Yeah,
don't-
thousands, but I don't know exactly how many to expect. We're hoping for a lot.
Yeah, it's a lot of energy. So yeah, EFT1 cost, the cost that we calculated and when we talked about this flight was around $370 million. That's the cost of the rocket plus pieces of the Orion that we're not going to reuse, you know, things we use one time. So that's basically the cost that we've been talking about. The rest, the capsule itself, we actually reuse. So we're going to use it in another flight test. And another key part about, I think, overall cost is, you know, if we were done with development and we had an Orion totally certified and we were making copies, it'd be very easy to say, okay, this copy cost me X million dollars. But we're in the middle of development. So it's not that we're just building software, we're actually developing the software processes and wringing out part. So it's part of what we call design, development, test, and evaluation, DDT&E. So we don't split DDT&E by flight. So we don't calculate it that way. We are, as part of a process for our stakeholders, we are doing an assessment. It's called Key Decision Point C. SLS went through it. You might remember there was a memo out from SLS after their PDR, where we'll do the same thing, and we will estimate and do independent cost estimates of our total cost through EM2. And so once we have that and we've done our independent estimates, that will be published as the full cost, both DDT&E and the cost of the flights through EM2. So we're in the process of really wringing that out. Yeah.
Hi, James Dean, Florida Today. I think for Mark, I wondered if you could just give any more sense of how big the stakes are for this mission, in the sense that you already described you're working on a second vehicle already. You've got, you know, the long gap, so a lot of time to work with from this mission to the next. So, you know, just in the unlikely event that things don't go well, how badly do you need, you know, the data from this to, you know, get a vehicle that you can fly for EM1? Or, you know, if you had just a worst case scenario where the heat shield just utterly failed, you know, does that, you know, going to be a major setback, or do you just have time to deal with it, you know, to keep on schedule?
Yeah. Okay, so good questions, because there's a lot to that question. Let me say, first of all, so this is a very, very important flight test for us, because we have great models, and we are fortunate in that we have some of the smartest people on the planet as part of this program, and who have a lot of experience with spaceflight. You need to take those designs and estimates and actually fly them, and see whether in the environment that we're flying there's something that you don't expect. So that's why it's so big. You know, we expect it to go fine, but you really have to fly it to test it out. Mike mentioned, as far as the next flight, and then I'll get to your contingency question. We've already started EM1. We started EM1 a year and a half ago, and a lot of that was started based on lessons we learned on building EFT1 long before we fly it, right? When you learn a bunch by building the first unit. We learned a bunch about building the first heat shield and some things that we want to do differently for the next one. We learned about things we can do cheaper. We learned about things we can do lighter. We learned about things that we can make the performance better. All of those things we rolled into EM1, which has already started about a year and a half ago. So, and I would say we're not sitting back with our feet up on our desks working EM1. I mean, we are slamming that. We are now working that one. We are on the critical path to get EM1 done. Team's working very hard. So based on the budget we have, we are working full time to get that next one done. So I don't want to confuse people. There's a lot of margin to get to EM1. There's not, based on the plan we have today. As far as what happens, it'll depend. It'll depend on what happens as far as what that means. We know EM1 is an unmanned flight. Already it's an unmanned flight, so there's not people on it. So it seems to me we could find something, very well could find something in EFT1 and still decide that we just go ahead and move on to EM1. We can fix those things, and it's still an unmanned flight, and we don't have to refly EFT1. But it'll depend on what we find. And the key about EM1 is now we're on the big rocket, too, so there'll be different environments and other things that we find. So, did that answer your question, James?
I guess if I attempt to be maybe a little more specific, I mean, clearly, again, the heat shield is the key focus of the test, right? So is that the thing where you're most hoping to get some specific, some real results that will inform the design of the next one? Or are there many other systems that, might be modified, as a result of what you see this week?
Yeah, great question. The heat shield is the one where we needed this orbit, right? This 3,600 miles, this 84% of the lunar entry velocity. That's what drove that specific parameter of the test. But the heat shield is only one system of many that we're really testing on this flight, these separation events, pulling the lasts off, jettisoning the fairings on the service module, and all the entry navigation and guidance, make sure the computers are working, survive the radiation, that all our guidance algorithms are correct, we're operating the RCS system correctly, all the parachutes deploy. All of those we've tested individually, certainly tested on the ground, but to see them actually work in the flight environment, that's what this test. So there's a lot of things other than just the heat shield that we're testing. So again, I do hope if there are unusual things in the environments with the vehicle and we have missed those in the models, I hope we'd learn them on this flight, because that's the whole idea. But if we do have a failure of something, we got to look about what it was specifically, and then we'll make a determination as to how that would affect the next flight.
Bill Harwood, CBS News, with two quick ones. The launch weather criteria for the Delta IV Heavy, were there any modifications or changes because this is EFT1 in terms of visibility requirements, for example? Number one. And number two, I'm still a little fuzzy on what real-time video we can expect from the spacecraft during the mission versus what's recorded on board. And if all else fails and we rely on what's on board, it's a question for Brandy. When would we expect you guys to get that back to put out on the satellite for those of us to see that day? So just some visibility questions.
So first question, I want to make sure I understand in terms of the launch constraints. You said in terms of visibility.
I just was curious, were there any differences for EFT1 versus what you normally do for Delta IV Heavy?
Sure.
Or is it just exactly the same?
Sure. There are some differences. Obviously, you can look at what's on top. It's going to be an unfaired type of payload that we're flying, which is different. So, it required us to do some extensive wind tunnel testing to make sure we understood that, as we're flying this type of payload, what the effects it would have on the rocket. So there was some work done there. There's a lot of mission unique type analysis work that we had to do because of this. How we do some of the commanding and the sequencing of the flight profile. There was some changes we had to do there to support some of the unique requirements of this mission. Also, from a hardware vehicle perspective, there were some unique requirements from an environmental control system that we had to meet for which required us to add another swing arm. We had to modify our swing arm so that we could provide them the environmental control systems that they needed to support their payload. And then, we actually had to do some structural changes to the pad itself, because we normally carry a 4 meter and 5 meter type payload, and the Orion payload is 5.5 meters, and so basically it was too small. So we had to basically modify our platforms to allow it to be able to accommodate that. So those are the type of changes we made in order to accommodate that. But for the most part though, the rocket is pretty much the same. It's just we had to do some unique analysis to support this mission. So does that answer your question?
Actually, it was extremely useful, but it wasn't really what I was asking about.
Oh, okay. All right. Well, so maybe okay.
It was useful. No, I was interested in the launch weather criteria for a Delta
the launch
IV. Is
weather
there any difference
criteria.
from a weather standpoint?
Oh, okay.
In terms of being able to see the spacecraft as you go uphill? That was one, and then and two was for Mark or just on what we're going to see during the mission.
So
sorry
but from the weather perspective, it's the same constraints we have. Obviously, lightning is something that we're concerned about. Precipitation, we can't fly through precipitation at certain altitudes. Those are constraints. We also have constraints with wind. If the weather right now is predicted to be, the winds aren't going to be too high, so we shouldn't have any trouble, at liftoff. But those are all the type of constraints from a weather perspective we're looking at. And right now, we don't expect to have any of those type of issues for us, but none of them are unique for this mission.
Yeah, do you
I
go
can
ahead.
take that,
Go ahead.
yeah.
Yeah, on the cameras. I think I know, but you
Sure.
should say it.
So we, of course, will have the great launch views that you're used to. Then once it gets going, we'll get, we think, views from the cameras on the service module that show us the fairings, the protective panels being separated. That's about 6 minutes in, and right after that, the launch abort system jettisons, and that uncovers the crew module, so we'll start getting views from the cameras inside the crew module after that, looking out the windows. So, sometimes we'll be in the dark, just like we are with the space station, and sometimes Orion will be rotating, so we'll be looking out to space rather than down at the Earth. But we're hoping to get some really good Earth views. And then we have an unmanned aircraft that's going to try and get video of the crew module coming down under the parachutes at the end of the mission as well. So hopefully we're going to have a lot of good video for you. A lot of it is kind of dependent on everything working right, just like the rest of the flight test. But for the recorded video, there's some about an hour into the flight that we're going to try and get down some of the recorded video of the launch abort jettison. And if we get that, we hope to play it for you by the end of the mission. But if we're not able to, of course, we'll get it out to you ASAP after splashdown. More questions here? We've got one back there. Okay.
Sawyer Rosenstein with Talking Space. A lot of people are comparing this to the early Apollo test missions, and some people are saying that, we've done this before with these. What makes this mission so special that, or what can we learn in particular from this mission that we can't learn from something, say, in Apollo? And also, after this, the focus switches a lot more to SLS, but what will be the future in terms of testing Orion?
I think the key difference between Apollo is that the inside of the capsule is totally different. And you can think of the computers themselves. We know how much computing power has changed since the 60s, so we have state-of-the-art computers on Orion that not only help this unmanned craft, but eventually allow the crew to have incredible access to the systems on board, which you'll need when they're further and further away from Earth and need to be more and more independent. The interesting things about computers now is although they are much more powerful, they're also more susceptible to radiation than the earlier computers. So we have a more powerful system, but it's susceptible to different kind of environments than the Apollo system. So I think it's a good example. We're flying this particular design, even though it's going through the same region of space, it's got a different capability and it's going to have different reactions to it. It's the same with the heat shield. It's bigger, as Mike said, the structure is different. It's going to react different. Same with the parachute system, has some fundamental differences. The back shell tiles on Orion are shuttle-like, where on Apollo they were more avcoat, right? So for mass, we got a shuttle-like tile. So again, it's state-of-the-art, and we're flying that state-of-the-art in the environment of space. So I expect to see some significant differences.
Hi, in the back, Rory O'Neill with iHeartRadio. First, to clarify to this liberal arts major, the 86% of lunar velocity, could you just explain what that term is? And the second thing is, on the radiation exposure, what's the concern and how much of an X factor is it? Do you know what to expect going out there?
So the full lunar, so if you were coming back from the moon, you'd have a certain velocity, and you're going to hit the atmosphere at that speed. And then you're gonna, and your heat shield needs to be able to handle that. Well, we're not gonna go all the way to the moon with the Delta IV Heavy. We need SLS to do that. But Delta IV does a great job of getting us close. So the 84 was really the where we could get to with the Delta IV Heavy, which is pretty darn close. And we actually are transitioning the physics of reentry. Change as you go faster. In fact, it becomes more of a radiative heating. This plasma behind the heat shield, or behind the shock layer, starts heating the heat shield differently, and you need to get fast enough to start seeing that. It's much different than an entry from LEO. So we needed to get to this region, and that's what Delta IV is able to do for us. So I hope it answered that question. And I'm sorry, what was your other question on that? Oh yeah, so we have a lot of systems that go out to geosynchronous orbit, got a lot of ComSats. So we kind of know what this radiation band looks like. The The difference is these particular computer chips, we've tested them on the ground in certain conditions. There's some universities that have some labs that can do that, but you really need to fly them to go through that. And what happens is this radiation can actually cause what we call an upset. It can cause a glitch in the data. The computers are smart enough to know if they've got funny data, and they'll stop and reset. So they're smart enough to do that. Our computers will reset. We actually have two computers. If they both reset, there's another memory system that lets those computers go, okay, I reset, but here's the state of the vehicle, because they need to know what the state of the vehicle is when they stopped. So we've accounted for that. But that's part of what you have to think through when you know this is the kind of environment you go through. And as we go to the moon, we're going to go through this region. So.
Saber, diversity in STEAM. I had a few different questions. First of all, in the trial by fire video, they mentioned the computers on board Orion performing 480 million instructions per second. Is there a way that you can translate that into like a more consumer-friendly statistic, something like
very fast.
in gigahertz?
I think that whole thing was an attempt to communicate to computer people how fast they were. I'd have to think about that.
Are there any parts of EM1 that you're holding off building while you're waiting for the EFT1 data? Is the Delta IV Heavy the only vehicle capable of making the flying to these altitudes? Or flying Orion to these altitudes, rather. And can you go into some specifics on the way that you're going to be collecting data on what would have been crew exposure to the radiation?
So we have, for this test flight, the Delta IV was the most capable system that we had that could get us that range of altitude, and the way Mark just described it is having that transition where you see the plasma heating behind the shock layer. That's where we're driving to. The Space Launch System certainly could, but we wanted to do this test before we were going to have the Space Launch System available to us. But it's the Delta IV is the largest thing we have today that could do that. We do have a lot of radiation sensors on board. That's a great segue, though, because it gives me the opportunity to let folks know that our student engineering design competition winners are around the side of the room here from the Governor's School in Hampton, Virginia. So Lockheed and NASA ran a competition, and one of the things we wanted to focus on was the radiation susceptibility. So we had teams all over the country and down selected to 5 teams that just in April at the Science and Engineering Festival in D.C. Announced the Governor's School as the winner. So they have designed a payload that's inside the capsule now that has a radiation monitor inside of several different shielding materials to look at how well can we shield against radiation for that. So that's a number of experiments that we're actually flying inside to demonstrate different material properties and different radiation shielding. And I'm glad you guys are here.
I think we can go over here now.
Hi, Ken Kramer for Universe Today and America Space for Mark and Mike. Can you tell us a little bit more about the actual schedule to build EM1 and when will it appear here? Can you also meet a December 2017 launch date? And the last question is more about the lessons learned. I understand you're considering changing the heat shield. What can you tell us about that? Thank you.
Well, I can speak to the schedule since I've spoken to it before. At this point, we have a lot of challenges to September 17, so we won't be there at September 17. A part of that was, as we talked about, getting EFT1 done. We learned a ton about getting it done, but some of it took us a little bit longer than we expected. And we've also added ESA as a partner, and they're doing a terrific job coming up to speed, but their delivery schedule also will push us past September. The exact date that we're going to hit, December 17. The exact date we're going to hit is still something we're working through, and because I know whenever we announce a new date, people are going to want to make sure that we have a lot of confidence in it, because you don't want to be changing that all the time. So we're working that with headquarters, doing an assessment of that based on the risks that we have today. And that's, again, part of that. That'll come out as the announcement after our KDPC. But it's not holding us up. We know in this year, we know exactly what we need to be working. We know what the critical path is, and every day we're working those off. So it's not, that decision and determination of the final date is not slowing us down. We're moving.
And we're machining primary structures for the next crew module. So those are out at our suppliers now being worked, so that within, I think they start showing up at MAF in March, and then we'll start assembling that capsule, and it's towards the end of the year, early 16, that we actually have another crew module showing up in Florida.
In the next year, yeah.
The heat shield trade. You want to talk heat shield?
Yeah, so we're, a lot of the discussion we've had is about what we learned when we built the first one. And when we built the first one, which will work great for EFT1, we learned that the material properties were a little different than we expected. It wasn't quite as strong as we expected that it would be. So when we're looking at that, we know that that is the material itself, the AV code itself. And as Mike talked about, the loads are pretty high for landing and entry, especially now it's on this composite structure. So the team's looking at a lot of things. One is to get more confidence in the material properties, find out why it was a little weaker than we expected, or look at other designs. And there's another way you can build a heat shield where you actually build it in blocks and attach the blocks to the heat shield, and then you've got some seams that you've got to fill. So we're looking at both, and the key thing is we're going to fly EFT1 and learn how that performed as well as a key part of it. There was a question about, are we waiting on anything? We're not waiting on EFT1, but we're certainly going to get the data from EFT1, and that'll help inform that trade.
Yeah, and part of that was just the manufacturability of the heat shield. It's the current form, which we refer to as monolithic, is really labor intensive, and you can't see it now, but if you saw it back 15 months ago or so, or even if you look at one of the Apollo Command modules that's around in the museums, you can see this little honeycomb structure. And you realize that this material is injected like a caulking gun into every single one of those little honeycomb cells. And then it's all machined, well, it's cured, and then it's all machined and spot repaired and all this stuff. So it's a very intensive process. So one of the things we look at for all of these systems is, are there manufacturing lessons learned? And that's where we're looking at whether blocks are a better manufacturing solution as well. We've done that on the primary structures. We've gone from the number of panels that we form that need to be welded together, changes in the weld process. So right now, each crew module we build is a little bit different because it's a little bit lighter. It's a different set of panels, and all of those are to help inform and improve the manufacturing capability.
Hi, Robert Perlman with CollectSpace.com. Mark, I may have misheard, but I think you said that one of the things remaining to be done is to close Orion's hatch. If that's true, what is left to be done inside? And a more general question, I don't think we've seen any photos showing or video showing what the inside of the EFT-1 Orion looks like. Can you basically describe, if someone was to look through the hatch, what they would see?
Yeah, so the hatch is on. And the launch abort system hatch is also on. So we were out there today, and it's all sealed up. So those are done. They're doing their last, we call it bridge wire checks. Just basically make sure the pyros are all set, right? And that's all. And we close out the last piece of paperwork. So that's all we have left to do. It's all really, really good. If you were to look inside the crew module, fundamentally what you'd see is the back shell, which is basically a structural component that lays out volumes where we put the computers, and the computers are mounted in there. Then we also have the thermal control system, so you'd see some valves and the tubes that keep the cold that supply cooling for the cold plates. That's what you would see inside. Then you'd see a couple of bags of flags and stuff that you normally fly on a mission like that. And then you see a lot of wiring because the computers inside are controlling the thermal control system, as well as the prop system and the other avionics that are, many of which is outside the vehicle. So that's what you'd see. We don't have seats, so to speak, but we do have mass simulators inside that make the vehicle feel like it had a seat there. You'd also see a mass simulator for the displays and control panel, because we're trying to make sure that we know how the structure reacted to that mass, because it kind of hangs off the structure. So you'd see a mass simulator for that. So that's the way it would look inside.
Eureka Rush, the Voice of America Russian service. I have sort of contingency question. What if things don't go with the SLS exactly as expected? What if there are some technical or budgetary issues resulting in the serious program delay? Will you be able to modify Orion so that it could fly as sort of autonomous space station, at least for a while, and continue being launched by Delta IV? Thank you.
Yeah, our plan is SLS. We need SLS to do these long-range missions, so we don't have any contingencies to use another rocket. Delta IV is great for this flight, but it won't do the other missions that we need.
Chris Aber with Diversity and Steam once again, and I know you mentioned some of the manufacturing processes and the heat shield already, but would there be any other areas of EM1 that you'd be just kind of hanging back and waiting for the FT1 data before you went ahead with?
The major systems that aren't flying are not as much because we're waiting on design data as it is we've just phased those later in the program for development because they're more associated with the human flight. So things like the displays and controls and some of the habitation equipment isn't flying on this flight, but that strictly has been a budget phasing discussion between us and NASA in terms of what gets developed when.
Okay, any other questions here? All right, then I think that will wrap up our briefing for today. But of course, as usual, you want to stay tuned to NASA TV. We've got a big day coming up tomorrow for L-1, starting at 6 a.m. Eastern Time with interviews with NASA Administrator Charlie Bolden. 10 a.m. we'll have our regular Space Station Live programming, and that'll be followed by another briefing at 11 a.m., a pre-launch briefing to go over the final details. And then we'll wrap it up at 1 p.m. with the NASA social. So stay tuned. And then in the meantime, you can also check out nasa.gov/Orion for real-time updates. Thanks so much.